Hello again. I'm here with a video related to using method of sections to find internal forces in some selected member of the truss. This is a very simple truss, as you can see. And the objective is here to find force in members, say EF, force in member CF, and force in member CV using method of sections, because there are two ways that you could find forces in internal forces in trusses: method of section and method of joints. Method of joints is more tedious because you have to look at each joint, the free body diagram of each joint, and then work your way in toward the joints where your forces are acting. But method of section is a shortcut. So first of all, we have to ask ourselves, where are these forces located? So let me just highlight these forces. So we're looking at this member EF, we are looking at this member FC, and we are looking at member BC or CB. Now, method of sections, basically what you do is that you have to cut through a section of the truss. You don't want to cut, in general, more than 3 members because you don't want to have more than 3 unknowns at a time. Not that you cannot have more than 3 unknowns. You could have more than 3 unknowns. But then you won't be able to find all the forces that you want. The other thing that you have to worry about method of sections is that as you cut a section, you ask yourself, do I need, before I cut the truss, do I need to figure out the reactions here at G and at A? And the answer is no, because you could cut this truss right through these 3 members. And by the way, you could cut at an angle or you could cut straight. And then you say, well, I have the option of using the left side of this truss or the right side of this truss. So if I use the right side, obviously I don't need to find the reactions at the pin here, G and pin A. So actually that's how we're going to approach this problem. The efficient way is to just use the right side of the truss. Let me draw the free body diagram of this section that we are interested. So we have an 800 pound here, we have a 600 pound here. Now I'm going to show you the exposed forces in member EF. And by the way, we always show these forces as if they are in tension. So if you show the forces pointing away from the member, that implies that the forces are in tension. And then we solve for these forces. If we end up getting a positive, that means the member is in tension. If we get negative, that means the member is in compression. So the reason we don't want to cut more than 3 members, because you're limited to 3 equations. Some of the forces in x equals 0, some of the forces in y equals 0, and some of the moment equals 0. So 3 equations, 3 unknowns. So basically this truss here is like a rigid body in equilibrium. So now the way we approach this problem, the method of section, basically you just want to use your moment equation as many times possible. So you could take moment about different points. So where is a good point to take moment to find one of these unknowns? For example, if you want to find the force in member EF, take moment about a point like C where these 2 unknowns are acting at, so they are eliminated. So by taking moment about C, I can go ahead and setting it equal to 0, of course, I can go ahead and find the force in member EF. So you see the moment of force EF about C times 4 feet. And then obviously 600 is that C doesn't have any moment. That leaves me the 800, which is going clockwise. So that would be negative. So look, I could find force in member EF easily. Comes out to be an 800 positive. 800 positive means this member, the direction that I have assumed is correct, and hence that member is in tension. Next, I say, okay, how could I find the force in member CB? Well, find the point where these 2 forces are going to be eliminated. So that happens to be force F. By the way, the point doesn't have to be on the member. It could be a point, away from the member, even though the force point F actually exists on the actual member. But after you cut it, is not part of the that free body diagram. But in any case, by taking moment about F, actually what we are doing, we are saying that FCF and FEF don't have any moment about. F. Therefore, that leaves FCB. So the moment of FCB about F is FCB times 4 going clockwise negative. Then we have 600 times 4, which is also going clockwise negative. And then, of course, we have 800 times 8 feet going negative equals 0. So if we solve for FCB, this time we end up getting a negative answer, negative 2200. And then we say, oh, this member must be in compression. So we say it's 2200 pound in compression. So far, member EF is in tension. So this member is in tension. And member CB came out to be in compression. So that leaves us with just one other member. That is member CF right here. So how do we find force in this member, CF? Well, we cannot use a moment equation. Well, we could use a moment equation, but not efficiently. Because first of all, you gotta find moment about a point where these two forces, FCB and FEF, don't have any moment, and they are parallel to one another. But you know what? We could use the force equation. Why don't we sum of the, add forces in the y direction and say it equal to 0, and balance forces in that direction. In that case, you'll see that the component of FCF in the y direction, notice that this is 4 feet and this is 4 feet, so this angle must be 45 degrees, right? So that would be FCF sine 45. We have a 600 going down here and an 800 going down, so that's 1400. So FCF becomes positive 1980 roughly pound. Because we got a positive, this member is also in tension. So I hope you enjoyed this video. Thank you as always for watching and listening.